Welcome to Math Tutorials. In this video, we are solving every question of exercise 5.1 of Chapter 5, Continuity and Differentiability, from the NCERT Mathematics textbook for Class 12, Part 1. Exercise 5.1 has 34 questions, all about continuity. Checking continuity at points, hunting for discontinuities of piecewise functions, fixing unknown constants so pieces join, and using the algebra of continuous functions on trigonometric and modulus combinations. Here is the full list. Question 1. We must prove continuity of the linear function 5x minus 3 at 3 separate points, 0, minus 3, and 5. At each point, we compare the limit of f with the value of f. Continuity means they agree. The test at any point c. The limit of f as x approaches c must equal f of c. At 0, the limit of a polynomial is found by direct substitution, and it matches f of 0. At minus 3, substitution gives minus 18 on both sides. And at 5, both the limit and the value are 22. All 3 points pass the test, so f is continuous at each. Question 2. A quadratic this time, 2x squared minus 1, tested at the single point x equals 3. Again, we compare limit against value. Substituting x equals 3 into the polynomial gives the limit. The function value is the same number, so f is continuous at 3. Question 3. 4 functions to examine. A polynomial, 2 rational functions with a point removed, and a modulus. Part A is a plain polynomial. Parts B and C are quotients. And Part D wraps a polynomial in the absolute value. Part A, every polynomial is continuous at every real number, since direct substitution gives the limit. Part B, on its domain x not equal to 5, the denominator never vanishes, and a quotient of continuous functions is continuous. Part C, factor the numerator. On the domain, the factor x plus 5 cancels, leaving the polynomial x minus 5. So part C is continuous at every point of its domain. Part D, the modulus function is continuous, and so is x minus 5. Their composition is continuous everywhere. Question 4. The power function x to the n must be shown continuous at the point x equals n itself. The identity function is continuous, and products of continuous functions stay continuous. X to the n is the product of n copies of the identity function x, each of which is continuous everywhere. By the product rule for continuous functions, f is continuous at every real number, in particular at x equals n, where limit and value are both n to the n. Question 5. A 2-piece function, the identity up to 1, then the constant 5 beyond. 3 points to test. Away from the junction x equals 1, the function agrees with a single simple piece. So the junction is where the interest lies. At 0, near x equals 0, the function is just x, so the limit is 0, equal to f of 0. Continuous there. At 1, from the left f is x, giving 1. From the right f is the constant 5. The one-sided limits disagree, so the limit does not exist. F is discontinuous at 1. At 2, near x equals 2, the function is the constant 5, so limit and value are both 5. Continuous there. Question 6. 2 linear pieces meeting at x equals 2, we must find every point where f fails to be continuous. Each piece is a polynomial, continuous on its open stretch, so only the junction can misbehave. For x below 2 and for x above 2, f agrees with a polynomial, hence is continuous there. At the junction, left limit from 2x plus 3, right limit from 2x minus 3. 7 is not 1, so x equals 2 is the only point of discontinuity. Question 7. 3 pieces now, with junctions at -3 and at 3, and a modulus in the first piece. Each piece is continuous on its own interval, so we only interrogate the two junctions. At -3, from the left, modulus of x plus 3 gives 3 plus 3. From the right, -2x gives 6. The value f of -3 is also 6. Both one-sided limits and the value agree, so f is continuous at -3. At 3, the left piece gives -6, the right piece gives 20. These disagree, so x equals 3 is the only point of discontinuity. Question 8. The sine function in disguise, modulus of x over x away from 0, patched with the value 0 at 0. For negative x, this is -1. For positive x, it is +1. The clash at 0 is the whole story. Resolve the modulus. For x below 0, f is -1. For x above 0, f is 1. On each side, f is constant, hence continuous. At 0, the two one-sided limits disagree, and neither equals the assigned value 0. So 0 is the only point of discontinuity. Question 9. This one looks like question 8, but watch carefully what the first piece equals for negative x. For x below 0, modulus of x is -x, so the quotient is a constant. For negative x, the modulus is -x, so x over modulus x is x over -x, which is -1. So f is the constant -1 on the whole real line. A constant function is continuous everywhere. There are no points of discontinuity at all. Question 10. A line meets a parabola at x equals 1. Both pieces are polynomials, so only the junction needs the two-sided test. At 1, the left limit uses the parabola, the right limit uses the line. Both equal 2, which is also f of 1. So f is continuous at the junction and everywhere else by the polynomial pieces. Question 11. A cubic hands over to a quadratic at x equals 2. The junction test again. At 2, the cubic gives 8 minus 3, the quadratic gives 4 plus 1. They agree with each other and with f of 2, so f is continuous everywhere. Question 12. A 10th power against a square, meeting at x equals 1. High powers of 1 are still 1, so the left limit is easy. At 1, the left piece gives 1 minus 1, 0. The right piece gives 1. 0 is not 1, so x equals 1 is the only point of discontinuity. Question 13. Two parallel lines, 10 units apart, switching at x equals 1. Parallel pieces cannot join unless the jump closes, so we test the junction. At 1, the left line gives 6, the right line gives -4. The jump of 10 never closes. F is discontinuous at 1 and continuous everywhere else, so f is not a continuous function. Question 14. A staircase of 3 constant values on the interval from 0 to 10. Constants are continuous, so the two junctions carry the whole discussion. On the interiors of the 3 stretches, f is constant, hence continuous. At 1, left value 3, right value 4, a jump. At 3, left value 4, right value 5, another jump. So the discontinuities are exactly x equals 1 and x equals 3. Question 15. A line, a flat stretch, and a steeper line with junctions at 0 and 1. Test each junction in turn. At 0, the left line 2x tends to 0, the middle piece is 0. They agree with f of 0, so continuous at 0. At 1, the flat piece gives 0 from the left, but 4x gives 4 from the right. 0 is not 4. The only discontinuity is x equals 1. Question 16. A flat floor, a rising line, and a flat ceiling. The pieces look designed to join. Check whether the line actually meets each flat piece at the junctions. At -1, the floor is -2 and the line 2x also gives -2. Continuous. At 1, the line gives 2 and the ceiling is 2. Continuous again, so F is continuous on the whole real line. Question 17. Two lines with unknown slopes A and B. We need the condition tying it to B that closes the gap at x equals 3. Continuity at 3 forces the one-sided limits to be equal. Left limit and right limit at 3, in terms of A and B. Set them equal for continuity. Solve 3a minus 3b is 2, so it is b plus 2/3. Any pair A, B with this relation works. Question 18. A parameter lambda scales the left piece, and we must ask whether any lambda makes f continuous at 0, then look separately at x equals 1. Careful here. The left piece vanishes at 0 no matter what lambda is. At 0, the left limit is lambda times 0 minus 0, which is 0 for every lambda. The right limit is 1. 0 can never equal 1, so no value of lambda makes f continuous at 0. At 1, the function is the single polynomial piece for x plus 1, so f is continuous there for every lambda. Limit and value are both 5. Question 19. The fractional part function, x minus its greatest integer, we must show it breaks at every integer n. The greatest integer jumps at each integer, and that jump transfers to g. Fix an integer n. Just below n, the greatest integer of x is n minus 1. At n and just above, it is n. So the left limit of g is n minus 1, which is 1, while the right limit and the value are 0. 1 is not 0, and n was any integer, so g is discontinuous at every integral point. Question 20. A polynomial minus the sine function plus a constant, tested at x equals pi. Polynomials and sine are continuous, and sums and differences of continuous functions stay continuous. X squared, sine x, and the constant 5 are each continuous everywhere, so their combination f is continuous everywhere, in particular at pi. Directly, the limit at pi is pi squared minus sine pi plus 5, and sine of pi is 0, matching f of pi. Question 21. Three combinations of sine and cosine, their sum, their difference, and their product. Sine and cosine are continuous on all of R, and the algebra of continuous functions handles the rest. The building blocks, sine and cosine are continuous at every real number. Part A, the sum of two continuous functions is continuous. Part B, so is the difference. Part C, the product of two continuous functions is continuous. All three functions are continuous on the whole real line. Question 22. Four trigonometric functions, cosine itself, and the three reciprocal functions built from sine and cosine. The quotient rule for continuity does the work. A quotient is continuous wherever its denominator is non-zero. Cosine is continuous at every real number. Cosecant is 1 over sine, continuous wherever sine is non-zero. All x except integer multiples of pi. Secant is 1 over cosine, continuous except where cosine vanishes. The odd multiples of pi over 2. Cotangent is cosine over sine, continuous except at the zeros of sine. Again, the integer multiples of pi. Question 23. Sine x over x for negative x, and the line x plus 1 from 0 onward. The standard limit of sine x over x at 0, from class 11, is exactly what the junction needs. Away from 0, each piece is continuous. A quotient with non-zero denominator on the left, a polynomial on the right. At 0, the left limit is the standard limit, 1, the right limit is 0 plus 1, also 1, and f of 0 is 1. Everything matches. F is continuous everywhere, with no points of discontinuity. Question 24. The wild oscillation of sine of 1 over x, tamed by the factor x squared. Sine is bounded between -1 and 1. That bound is the key at 0. Away from 0, f is a product and composition of continuous functions, hence continuous. At 0, bound the function. Sine of anything lies between -1 and 1, so f is squeezed between -x squared and x squared. Both bounds tend to 0 as x tends to 0, so the limit of f is 0, which equals f of 0. Continuous everywhere. Question 25. Sine minus cosine away from 0, with the value at 0 pinned to -1. The question is whether that pinned value matches the limit. Away from 0, f is a difference of continuous functions, hence continuous. At 0, the limit is sine 0 minus cosine 0, which is 0 minus 1, exactly the assigned value. So f is continuous everywhere. Question 26. A quotient of k cosine x by pi minus 2x, with a hole at pi over 2 filled by the value 3, k must make the pieces meet. Substituting x as pi over 2 plus h, converts the limit into the standard sine over angle limit. Put x equal to pi over 2 plus h, with h tending to 0. Cosine becomes minus sine h, and the denominator becomes minus 2h. The quotient simplifies, and the standard limit sine h over h equals 1 gives k over 2. For continuity, this limit must equal the value 3, so k is 6. Question 27. A parabola scaled by k must land exactly on the constant 3 at x equals 2. One equation from the junction gives k. Left limit k times 4, right limit 3. Equate 4k equals 3, so k is 3/4. Question 28. A line with slope k must meet the cosine curve at x equals pi. Cosine of pi is -1, which sets the target for the line. Left limit k pi plus 1, right limit cosine pi, which is -1. Equate and solve for k. Question 29. Two lines must agree at x equals 5. The right-hand line fixes the meeting height. Left limit 5k plus 1, right limit 15 minus 5, which is 10. Equate 5k plus 1 equals 10, so k is 9/5. Question 30. A line segment at x plus b must bridge the flat value 5 at x equals 2 up to the flat value 21 at x equals 10. Two junctions give two equations in R and B. Continuity at 2, the line must take the value 5 there. Continuity at 10, the line must take the value 21 there. Subtract the equations. 8a equals 16, so it is 2, then b is 5 minus 4, which is 1. Question 31. Cosine applied to x squared, a composition of two functions. A composition of continuous functions is continuous, so we name the two layers. Write f as g composed with h, where h is the polynomial x squared and g is cosine, both continuous on R. The composition of continuous functions is continuous, so f is continuous at every real number. Question 32. The absolute value of cosine, again a two-layer composition. This time the outer layer is the modulus function. Write f as g composed with h the cosine and g the modulus, both continuous everywhere. Compositions of continuous functions are continuous, so f is continuous on all of R. Question 33. Sine of the modulus of x, the same composition idea with the layers swapped. Modulus inside, sine outside. Write f as g composed with h, where h is the modulus and g is the sine. both layers are continuous on R, so the composition sign of modulus x is continuous everywhere. Question 34, the last one. The difference of two modulus functions, each with its own corner. Both pieces are continuous, so the difference should be 2. Writing f piecewise confirms it concretely. Modulus of x and modulus of x plus 1 are both continuous on R, so their difference is continuous on R by the algebra of continuous functions. Concretely, resolving the two moduli over the three ranges gives a piecewise form whose pieces meet. Value 1 up to -1, then a descending line, then -1. At -1, both sides give 1. At 0, both sides give -1, no jumps anywhere. F has no point of discontinuity. That completes all 34 questions of exercise 5.1. In the next video, we will take up exercise 5.2, where differentiation enters the chapter. Thank you for watching. If you found this video helpful, do like it, subscribe to math tutorials, and share it with your friends.